Yeah.
Okay.
Good afternoon, everyone. It's my great pleasure to invite Professor Peter Lassen to give us lectures. He is from University College London, which top university around the world. And Professor Lassen is a famous scientist in the field of computational neuroscience. He has published very good papers. Now, let's welcome our professor to teach us computational neuroscience. Welcome. Okay.
Hi, everybody. Can't see anybody, can I? Okay, let's put this up here. So the class is an hour and a half. Is that right? Okay. Okay. Okay, so let's start with a big picture, and then I'll tell you what I'll be talking about. And this is a really big picture, zoomed out. So here we have your brain. It takes input. What's going on here? So it gets sensory input, vision, touch, hearing. And on the outside, it produces motor output. And in between are a bunch of neurons. So the human brain has about 100 billion neurons. Larger than ChatGPT. And somehow those neurons transform sensory input to motor output. But it's not just a hodgepodge of neurons. In fact, the brain is divided into, lots of different areas. Okay, visual areas, auditory areas. And these areas are all connected to each other in a very complicated way. So the modern view, and so in some sense, neuroscientists want to understand how the brain works, and how the brain works really comes down to how do a bunch of neurons transform sensory input to motor output. So in the modern view, sort of the modern view of networks, so the weights, the connection strengths, we call them weights, and we'll be explicit about what that means later, but I'm sure you've heard about these weights. So weights are everything. Okay. When they train deep networks, basically they start with some random connected weights, and then they train them, and then initially the networks don't work at all, and eventually they work very well. It turns out, if you've ever trained a deep network, so the initial weights really matter. They're pretty important. And the reason is kind of obvious. If you say, let's take a feed-forward network. Okay, you get some input, some output. And in between, you have some weights. So if the weights are too small, so you have some connection strengths, weights. So if too small, no information flows through the network. Okay. Yeah, the weights are really small. You start off here. By the time you start off here. Uh-oh. Let me. Okay, here we go. So you start in this input. By the time you get to the output, there's nothing there. Okay. If the weights are too big, then you get basically too much amplification. So by the time you get to the output, where everything is too big. So what we're going to do in the first part of the first couple lectures, so the first couple lectures, the focus is going to be on the initial weights. So initial weights in a network of spiking neurons. Okay, which may seem like not super interesting, but it's complicated for several reasons. One, the networks are recurrent. And basically it means they're not feed forward. Okay. Networks are recurrent. So basically what you have is a network of neurons, and you might get some input from external input, but also this neuron connects to that neuron, which connects to that neuron, which connects back to that. Okay. So it's not a simple feed forward structure. Neurons of the brain are highly recurrent. And there's also lots of feedback, which we won't talk about. The other thing are networks is neuron spike. Which I'm sure you've already seen before. They're not just analog units. And there's also something called Dale's law, which you may or may not have encountered, which basically means neurons are either excitatory or inhibitory, but not. Okay. And so these three things make even the initialization, the activity initialization, kind of complicated and also kind of rich. Okay. So that's what we're going to focus on, initial weights. And really what that means is we're going to consider a randomly connected network of recurrent spiking neurons that obeys Dale's law. Oh, before I forget, a couple things you do need to know. There's lots of information on the website, which is HTT. I'm sure that Shangbin will tell you this. Here's my website. Okay. www.gatsby. .ucl.ac.uk /delta. Okay. So remember that I'm going to put all my lectures on there, the recordings, which will be on a YouTube video, and the slides. So that's, and also extra reading. So that's where you can get all the material. A couple of things before one more thing before I start. So the math thing I'm going to use is not super sophisticated, but there are a couple things you need to know. So one is linear ODEs. Which is ordinary differential equations. So basically, you should be able to solve an equation like this. Tau dx dt equals minus x plus a e to the minus d over tau s, a different number. 2, you should know about Taylor expansions. I assume you guys know this, or at least have seen it. 3, you should know the central limit theorem. That will be used later. And 4, a linear algebra, which basically means eigenvalues and eigenvectors matrices. Pretty much all we know, all we're going to need. And eigenvectors of matrices. Oh. Okay, so you should be familiar with all those. And if you, that's all you pretty much all you need for what I'll be talking about. One more thing is I should give you my email address. My email If you have any questions, feel free to email me. So PL@gatsby.ucl.ac.uk. Okay. It's also on the my email address is on the website. So if you have any questions, feel free to email me. And you should also feel free to interrupt during my lecture. I'm very, very happy to take questions. I'm guessing, at least in some places, I'll go too fast. So you're much better off interrupting me than getting lost. Okay, so let's start. I'm going to start by writing down an equation that I think you have all seen. Okay, this is an equation for the membrane potential of a neuron. So VI equals membrane potential of neuron I. So in a network of n neurons, okay, where n is some large number. You can think of 1,000,000, 100 million. It's a big number, lots of neurons. And so the memory potential is tau dvi dt equals minus vi minus e leak. Now, I assume you've seen this before, but I'll spend a little time on it anyway. Minus a sum on j wij. I'm going to call it wij tilde gj of t vi minus ej. Okay. So I'll explain all these terms. This is a linear integrate and fire neuron. And fire. And fire. Neuron. So it's linear because it's linear in V here. So this is linear in V. You can imagine it replaced by something more complicated like Hodgkin-Huxley. And it fires, well, we'll see what it fires. So this is the subthreshold behavior of the neuron. And let me explain all the terms here until I clear what they are. This is a time constant. So tau is about 10 milliseconds. So it's a characteristic time of neurons. So this is the leak potential. Leak potential. So it's around minus 65 millivolts. So this is the reversal potential. Let's say a few more about that. Reversal. In a few seconds. So this is the weight. Okay. And GJ is sort of where the interesting things go. So GJ is conductance change. conductance due to spikes on neuron J. So the picture we should have is here we have this neuron, this is our neuron I, and then connected to it are lots of other neurons. So this is J equals 1. So these are the J neurons. So these are presynaptic neurons. This is postsynaptic. And you have all these neurons are connected to our neuron. Okay, and the connection strength is this weight. Okay, these WIJs tell you how long strong it's connected. And basically, whenever neuron J fires a spike, the conductance G sub J changes. Oops. So if we, on this axis, we have time. On this axis, we have GJ of T. Okay, and these are spike times. These are spike times. So these are all the times on neuron J. So every time neuron J spikes, what happens is that the memory, this GJ, the conductance goes up. It comes down, goes up, comes down, up, down, up. Okay. And when this conductance goes up, when it's 0, of course, neuron J is having no effect on the memory potential of a neuron I. When it spikes, it now neuron's affected. Okay, so that's a picture. So that's all these terms. Now there's one more thing you need to know, and that is, so this is basically, if you look at what, so what's, let's draw a picture. Hold on a sec. Okay, good. So here's our equation. GJs are spikes. So what we're going to do is we're going to focus for a second on this term. Okay. That term is going to be some time varying okay, so that's going to be some time varying term. And now we're going to plot V sub I. Okay, so So this is VI of t. So if you go back to this equation, if this term here is 0, if none of these neurons are spiking, okay, in that case, tau dvi dt is just driven by this, and basically the voltage relaxes to the leak potential. Okay. So if we go over here, red. So this is when this is a regime where, so this is minus 65. Remember, that's the leak potential. And if no neurons are spiking, the neuron just sits at minus 65 millivolts. Okay. This term here is 0. No neurons are spiking. It just sits at minus 65 millivolts. Okay. And what happens when they spike? Let's actually take this and copy it. Okay, let's copy it. Copy. Paste. Put it down here so we can look at it. Let's say, so EJ, I'm going to tell you about the reversal potential. So EJ is reversal potential. It's kind of important. So if neuron J is excitatory, then EJ is approximately equal to 20 millivolts. And if neuron J is inhibitory, then EJ approximately minus 80 millivolts. Okay. So if EJ is, let's say, an excitatory neuron spikes, that means, so excitatory neuron spikes. So what happens? What happens is that this term is positive, right? Excitatory neuron spikes. This term here is positive. Right? Because EJ is plus 20, so we have minus, so VI, remember, is about minus 65. So this is about minus 65. EJ is 20. Minus 65 minus 20 equals minus 85. And you combine it with this minus sign here, gives plus 85. Okay. So what happens when the presynaptic neuron fires, this goes up. Hold up. Inhibitory neuron fires, it goes down. So this is, as the neuron fires, fluctuates around. And the reason this is called an integrate and fire neuron is because in this model, at about minus 50 millivolts, the neuron spikes. So when it hits minus 50, it generates action potential, and then it goes back down. Okay. So this is the integrate part. Okay, when it's below minus 50 millivolts, and this is a fire part. When it hits 50 millivolts and generates a spike. So we went back to this picture here, all these spikes. All these spikes right here, spike, spike, spike. That's when neuron J's memory potential went above minus 50 millivolts and it generated a spike. Okay. So this is a picture. This picture is very important. Okay, so down here we have all the other neurons in the network are spiking. Those spikes are causing this memory potential to fluctuate. Eventually it reaches threshold and it generates a spike. So this is our model of our network. Okay, so it's pretty complicated, right? We have maybe 1 million or 100 million neurons all generating spikes, all causing each other to fire. And what we want to do next hour or so is, in some sense, get intuition into what's going on in the network. Okay, it seems like kind of a hard problem. We're going to simplify it a little, and then we're going to use the fact that networks, the weights are randomly connected to make our life really simple and get some intuition into how this works. Okay. So I sort of alluded to, I assume you guys have heard Dale's law before. Dale's law, in its simplest form, so Dale's law, in some sense, this is Dale's law. Dale's law really just says that reversal potential, so the reverse EJ depends on neuron J. Okay, and what that says is if neuron J is, remember, the presynaptic neurons. If we go back to this picture, so this is presynaptic neuron J. So if E sub J is positive, plus 20 millivolts, meaning neuron J is excitatory, then it excites. It doesn't just excite that neuron; it excites a different neuron. So I prime, right? So when this neuron fires, if it's excitatory, it excites all the neurons it's connected to, which is kind of a weird property. Nobody knows why that's the case, but what that means is a neuron is either excitatory or inhibitory. It's never both. Okay, very different from standard deep network. So Dale's law is actually going to be kind of a big deal. Okay, so we're gonna solve this to varying degrees, and the first thing we're going to do is make an approximation. So this is called so this model here. Oops. So this here is called a conductance-based model. And the reason it's called a conductance base is that whenever a neuron fires, the conductance changes, and it's pulled toward the reversal potential. Okay. That actually mathematically is a little bit hard to analyze. Oops. So we're going to switch to a current-based model. And what we're going to do is, remember we had this term, actually, I think, good. Okay, so what we're going to do is make kind of an approximation. Okay, so if EJ, so we're going to switch to current base model. So if EJ equals 20 millivolts, meaning neuron J is excitatory, in that case, we're going to let Wij tilde Vi minus EJ, and put the minus sign out here. We're going to replace this by Wij E. And this is going to be some number that's greater than 0. Okay. And if EJ equals minus 80 millivolts, which means neuron J is inhibitory, okay, we're going to let minus Wij Vi minus EJ. So now we're going to let this go to minus Wij I, and Wij is also greater than 0. Okay. When we do that, our model becomes tau dvi dt equals minus Vi minus E leak plus the sum on J of Wij E Gj of T minus the sum on J of Wij Gj of T. Okay. And let's complete this model so we have it written down when Vi of T reaches minus 50 millivolts, spikes, and it's reset to minus 65 millivolts. Okay, so this is our model. Okay, and I guess the last thing we need to know, just to be clear, is so remember when a neuron spikes, So GJ of T goes up. The neuron J spikes. Okay. And the picture you should have in mind for that is this right here. Okay. The neuron J spikes at these spike times, GJ goes up. Okay. Okay. So that's the model we should have. And this is the model we're going to work on. We're going to use for the rest of the next couple lectures. Using current basis approximation, but it's a reasonable one. And it's much easier to deal with mathematically. So this is not a bad model of the brain. And so we want to analyze it. So we're about halfway through. Let's take a 5-minute break. You guys can ask me questions during this time. You can email a question this time. If you're anything like me, my brain fills up after a while, so we'll take a quick break. And back in 5 minutes. Okay, so let's continue. This is the equation we want to solve, and it's kind of complicated. A couple things we need to know, though, that's going to help our life a little bit. So in this sum here, so let's actually write down this sum. So let's kind of concentrate on excitatory neurons only for a second. We'll consider the other inhibitory neurons as well. But in this sum here, sum on J, I'm going to write J equals 1 to the number of excitatory neurons in the network, which is going to be large, Wij Gj of t. Okay. So, although you could have a network with 1 million neurons, so each neuron connects to about 1,000 other neurons. Okay. So even though there are a lot of terms in the sum, NE can be large, there are actually only about 1,000 non-zero terms in. Okay. Okay, so that's fact number one. Important fact number one. Two, neurons in the brain. Fire at about 1 to 2 hertz. At spikes per second. On average. Okay. So what do we have here? We have a postsynaptic neuron. This is our neuron I. It's getting input from about 1,000 other neurons. Firing at 1 to 2 hertz. So this neuron is getting an input about 1 to 2,000, 2,000 spikes per second. Okay. If you count up all its presynaptic neurons, it's seeing a lot of spikes. Okay. So if you look at what its input is, so the input to neuron I, so this is, so what we're going to do is plot input to neuron I I'm going to call this is going to be time. Call this 0. I'm going to call this 10 milliseconds. So in 10 milliseconds, it sees about It sees about 10 spikes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, it sees 10 spikes. And so what happens is these spikes, they go up. So there are some fluctuations, right? So the input, it sees 10 spikes, there's some fluctuations, but the average is, the average is not So we're going to take the average. Okay. So this quantity here fluctuates in time. Okay. But its average, because there are so many spikes, its average is not changing so much. So this term here, so basically what I plotted on this axis is the sum on J, sum on J of Wij E Gj of T. That term is fluctuating. That's the green curve. The blue curve is its average. The average. Okay. There can fluctuations around that average, but they're not, they're kind of big, but they're not so big. So one of the things that we do a lot in neuroscience is make really strong approximations. So what we're going to do is we're going to approximate. So here's a big approximation as a first pass. We're going to drop this later on. So we're going to approximate sum on J of Wij J of T by its average. Okay. It's a huge approximation, but it turns out actually it gives us a lot of intuition into what these networks are doing, and we're going to drop it later on. Okay. And so that massively simplifies things. Okay. So we're going to actually now use a specific form for Gj of T. So basically, we're going to write sum on J of Wij with E here, Gj of T. We're going to replace this by the sum on J of Wij E. By the time average of Gj of T. Average over time. Okay. So what does Gj of T look like? So Gj of T is equal to sum on, let's say, K. We'll call it F of T minus Tj. Okay. So this is time of the K spike on neuron J. Okay. So remember we drew this picture. These were spike times in neuron J. Neuron J. So we're going to call this, we'll just give these names. So this is TJ1, this is TJ2, and so on. Okay, and what's F look like? So F of tau, or F of T, is just something that goes up and comes down. Okay, so this is T equals 0. So f of t, sometimes we use instantaneous rise and decay. Okay, so this is f, this is t. And what we're going to demand is the integral from 0 to infinity f of t dt equals 1. Okay, this is kind of important. What we often take is f of t equals e to the minus t over tau sub s divided by tau sub s times theta of t. So theta of t is a Heaviside step function. This is 1 when t is greater than or equal to 0, and 0 when t is less than 0. So basically, this is an instantaneous rise and decay, but it doesn't really matter. What we really care about is this integrates to 1. It's just a convenient normalization. Okay, so what we want to do is now compute the time average of this. Okay, I'm going to compute this time average. And the time average is basically average of Gj of t over time is equal to 1 over t. We're going to let t be really big. Integral 0 to t dt Gj of t. Let's go back to what Gj of t is. So Gj of t is this function here. It's the sum of all the spike times. Okay. So this is equal to 1 over t equals 1 over t integral 0 to t dt, and then the sum on k f of t minus t j k. Okay. So basically, it's an integral of, well, it's the integral of we're basically adding up all these little blips. It's the integral under this curve. So it's this integral. Okay. And remember, each of these things here integrates to 1. Okay. So this quantity here is really just we can write this as 1 over t integral sum on k of the integral from 0 to t f of t minus t j k. Okay. And this is basically each of these integrals. Oops, what happened? So each of these integrals is 1. So this is basically its count spike. This is number of spikes on neuron j and time t divided by t equals a firing rate of neuron j. Okay. So the reason we chose this normalization is so that the average value of Gj of t is going to be 1. And now the average value of the sum on j of w I j e Gj of t average over time is equal to sum on J of Wij times nu J. I'm going to put an E here so we know it's excitatory. Okay. So this is kind of nice, right? So that what that means is with the average drive to a neuron, let's go back to this equation. We're going to replace these things by, instead of this time varying quantity, we're going to replace this and this by the averages. Okay. So we're going to write, actually, let's go back here. Oops, I'm not sure what happened. Write it again. So we have tau dvi dt equals minus vi minus e leak plus the sum on J of wij e dje of t minus the sum on J I gji of t. Okay, we're going to now approximation is to replace these by time averages. Average over time. Average over time. So it's an approximation. And when we do that, this goes to minus vi minus e leak plus the sum on J of wij nu je defining rate of neuron J minus the sum on J of wij nu. Okay. So let's so we have tau dvi dt equals this. So this finally is an equation we can solve, and remember, so neuron I spikes when it hits minus 50 millivolts. Okay, so this is an equation we can solve. This is we're going to assume constant firing rates. So what we'll do is assume constant firing rates. Assume constant firing rates. And remember, neuron spikes. When it reaches minus 50 millivolts. So the picture we have is that, let's say that this term here, let's say this is positive. So what happens to the voltage in that case, if we plot Vi versus T, Vi of T versus T, so this is minus 65, this is minus 50. So what happens is, if positive, it gets pulled up, pulled up, pulled up, pulled up, pulled up. it hits minus 50. It emits a spike, comes back down. Spike is actually much higher, but I ran out of room. It's up again. It's a spike, it comes down. So it fires very regularly because the input is constant. Talk about that later. And what this is call this time TS, S for T spike. Okay. So the firing rate of neuron I, so nu I equals 1 over T spike. Okay. So what are we going to do? We're going to calculate the firing rate of neuron I, given that we knew the firing rates of all the other neurons in the network, and then we're going to make some approximations and do that to figure out the average firing rate of all the neurons. Okay, so that's a program. Given this differential equation, and assuming that this is positive, we're going to compute the firing rate. So that involves a little bit of math. Let's call this positive. Let's give it a name. Positive. We're going to call this V0. So this whole quantity here, this has a name. It's called V0. And we're going to solve the equation. Tau dvi dt equals minus vi minus leak plus V0. Okay. Initial conditions, so Vi at t equals 0 equals E leak. So basically our initial condition, is this point right here. So we'll call this t equals 0. So we'll call this point t equals 0. And at t equals 0, we're sitting right at the leak potential. Okay. So this equation has a solution, which you should check. Vi minus E leak equals V naught 1 minus E to the minus T over tau. Okay. And you can verify that. So when t equals 0, Vi equals E leak. Because when t equals 0, this whole term is 0. Okay. And then when t goes to infinity, Vi minus E leak equals V naught, which is exactly what we expect from this equation, right? At t goes to infinity, dv dt eventually goes to 0. And so Vi minus E leak equals V naught. Okay. So this is the right solution. You should verify it. And remember, so neuron spikes, the spike occurs when Vi equals, I'll call it theta, threshold equals minus 50 millivolts. Okay. So we have theta, so spike time, theta minus E leak Just remember this thing is 15 millivolts. Equals V naught 1 minus e to the minus t spike divided by tau. Okay, that's when the spike time occurs. Divided by V naught. I'm going to call this thing, find that to be delta V. Delta V is distance between threshold and between rest and threshold. So we have delta V over V naught divided by V naught equals 1 minus e to the minus t spike over tau implies e to the minus t spike over tau equals 1 minus delta V over V naught. Take the log of both sides and you get t spike over tau equals minus log 1 minus delta V over V naught. Or the frequency, the firing rate of this neuron now, nu I equals 1 over t spike is equal to tau 1 over tau log 1 minus delta V over V naught with a minus sign. Okay. It's a firing rate of a linear integrating firing nerve. So you should verify that. One thing we need, clearly we need to V naught bigger than delta V, which kind of makes sense. That's just picture. So the asymptotes, remember at the time goes to 0, the biggest this thing could be is V naught. So we better have V naught greater than delta V. Kind of should make sense. Okay. Okay, so that's a firing rate of neuron I. Let's make another approximation. I mean, it seems like we're making a huge number of approximations. Eventually, things are going to break down. Surprisingly, when we consider the more realistic case, all these approximations turn out to be completely fine for reasons that are not obvious. Okay, so what do we have? We have our equation looks like the firing rate of neuron I so the firing rate of neuron I, oops, let's switch to black. The firing rate of neuron I equals minus 1 over tau. So 1 over tau, by the way, because tau is 10 milliseconds, this is 100 hertz. Because tau equals 10 milliseconds. Divided by minus, well, oops, minus that. Minus log 1 minus delta V would be naught. And V naught is equal to sum on J of W E minus sum on J W yeah. So now here's another approximation we're going to make. So Wij equals We. Wij equals Wi. So basically, all weights are the same. So all excitatory weights are the same. And all inhibitory weights are the same. Okay, so basically every single neuron, excitatory neuron has the same weight, every single inhibitory neuron has the same weight. So what that means is all the neurons, well, all the neurons are basically the same. So all the neurons have the same firing rate. Have the same firing rate. Well, I have to be careful about that. Let's be a little more careful. Let's write it like this. So nu IE just equals nu E. And nu II just equals nu I. Okay. So all the inhibitory excitatory neurons have the exact same firing rate. All the inhibitory neurons have the exact same firing rate. And this equation here, this equation here turns into two equations, which I will write down. So right now we have nu E, firing rate of neuron E is equal to 1 over tau divided by minus log 1 minus delta V divided by WE nu E minus WI nu I. Actually, let's go back. All the firing rates. And then nu I equals 1 over tau. Okay. So this is a major simplification. So actually nu E equals nu I in this case. We're gonna make things a little more complicated later on, so it doesn't quite hold. But in a really, really, really insanely simple case, where all the weights are the same, there's only WE and WI, only two weights. All the neurons have the same firing rate, and we can write this as nu equals 1 over tau over minus log minus log 1 minus delta nu delta V over WE minus WI. Okay. So we have one equation we have to solve. Things are going to turn out to be a little more complicated, but what I want to do probably for the next 20 minutes is figure out how big are the weights. Okay, so this is kind of an abstract equation. How big are the weights? And by the way, I just realized I kind of made a mistake. So let's look at this term. Definitely made a mistake. So let's look at this term here. Go to the next page. The sum on J, W, A, J, E, mu E. That, remember, went to the sum on J of W, E, mu E. Okay. But remember, as I said, there are about 1,000, we'll call it K non-zero terms, non-zero weights. Okay, where K is about 1,000. So this sum here is basically goes to K W E nu E. Okay. So there's a K that I forgot in here. K goes here. K goes here. And K goes here. So the K is pretty important. There are K weights and K is about 1,000. Okay. Okay. So how big are the weights? For that, we need some actual, so far we've just been doing math. For this, we need some actual neuroscience fact. And that is, if you record it from a neuron, do you have some neuron? Oops. So if you do an experiment and you record from this neuron, record the voltage from this neuron versus time. So this is minus 65 as rest. And there's some single presynaptic neuron that's connected to it. And this neuron spikes. Let's say it's excitatory. What you'll see is that the memory potential goes up, comes down. Okay. And this height here is called V EPSP. Is in the order of 1 millivolt. And that's true for inhibitory IPSPs as well. So the IPSP is also in the order of 1 millivolt. Maybe half a millivolt, maybe a little. Okay. So we're going to use that fact to estimate the weights. And we're going to go back to our equation, but we're going to consider it just a single presynaptic neuron. So tau dv dt equals minus vi minus e leak. And then plus, we'll say it's an EPSP plus W I J E GJ of T. Where GJ of T is going to be a single, so minus, so no, there's no sum anymore. And the reason there's no sum anymore is because we're only considering a single neuron that spikes. So GJ of T is going to be 1 over tau sub S e to the minus T over tau sub S times theta of T. So GJ of T, this basically just goes up like this and comes down. So this quantity here is our time course. So this is t equals 0. Okay. I'm just going to give this, so what we want to do is solve for VI of t, the memory potential. So we're going to solve the equation tau dVi dt equals minus VI minus E leak plus Wij E e to the minus t over tau sub s divided by tau sub s. Okay. So this is an equation that I wrote down earlier. I'm going to write down the solution. We do a little bit of algebra to show that it's correct, and I want you guys to verify it. It's kind of important. So this actually, I think it's called the homogeneous inhomogeneous solution. It's been a long time since I knew those names. So we write VI minus E leak is equal to A times E to the minus T over tau. So that's the solution to this equation if there were no driving term, and then plus B E to the minus T over tau sub S. So we want to find A and B. So our goal is to find A and B. Find A and B so that VI minus E leak, the V so that VI at T equals 0 equals E leak. Okay. So we'll just find those. So we're going to take this. We're going to take this solution and stick it into this equation. Okay. So what happens when we do that? So first of all, we're going to consider this term first. So tau dVi dt of this term is going to equal minus A e to the minus t over tau. Tau dVt of this term is minus B. Oh, sorry. Sorry, guys. There's a fire drill every Monday. Minus B tau divided by TS, tau S, e to the minus t over TS, tau S. So that's what happens when you take the derivative. On the right-hand side, when we look at this term, we have equals minus A e to the minus t over tau, and then minus B e to the minus t over tau sub S. By the way, tau sub S is about, this is 1 to 5 milliseconds. And remember, tau is about 10 milliseconds. Okay. So that's that term. And then we'll add in this term here. So that term is plus Wij e to the minus t over tau s over tau s. So I just realized I'm out of time. I'm going to stop here. Oh, come on. Okay. I'm going to stop here. I'll continue on Wednesday, but as an exercise, fine. So VI minus EL max, let's say equals 1 millivolt. How big is Wij? Okay, so that's what we're going to do next time. Sorry about the fire alarm, and I'll see you guys next Wednesday. Okay, see you guys next Wednesday, and we'll finish.
Bye
this.
bye.
Goodbye. There's something in the chat. Oh, I don't see the chat.